we continue our discussion on transistor, and now we take the two current gains which we often encounter with the transistors. The one is called alpha. Alpha is the current gain which is observed in common base circuit, that is CV circuit. And this is defined because at present we are considering the DC signals. So, we define alpha DC as the ratio of, as I said earlier, that for gain the fundamental definition remains the same, output versus input. When we talk of current gain, then it is output current to input current and in the CV circuit, common base circuit, you will recall that the output current is collector current and input current is the emitter current. So, always remember that the current gain alpha is for common base circuit and we define it as the ratio of collector current to emitter current. We also will recall what we have said earlier, that emitter current is slightly higher than collector current. Most of the electrons in a NPN transistor, they cross over to the collector region and finally they are collected, but a small portion of the electrons get recombined in the base region, which constitutes what we call the base current. So, alpha DC is very close, but less than unity. And let us see as an example that if I see the collector current is 4.9 milliampere and this is produced by a emitter current of 5 milliampere, then alpha DC is 4.9 milliampere by 5 milliampere. So, this is equal to 0.98, close to 1, but less than 1. And common base circuit is important case when we talk of the working of transistor and in many other situations. So, alpha DC is a fundamental quantity that we will remember, but it is less than 1. So, in fact, in common base there is no current gain. In fact, because output current is less than the input current. So, there is a power loss in fact, but still because of this ratio is always called as current gain. So, we call it the current gain. Then there is another current gain which is called beta, current gain beta, and as we are discussing the case of DC. So, we call it beta DC, and beta DC is the current gain in common emitter circuit, in common emitter circuit. Always remember, alpha is the current gain in common base circuit and beta is the current gain for common emitter circuit, and the output current here again is the collector current and the input current is now IB, the base current. Base current is very small in comparison to the collector current. Therefore, this is very high. This can also be defined in terms of the change in delta B, delta IB is the change in the base current, and if this gives rise to change in the collector current of delta IC, then this ratio, this is actually the way we can define and we can find out experimentally the value of the current gain beta. And so, this is current gain and this is very high. Now, let us take as an example that IB of say 0.06 milliampere produces a collector current in common emitter circuit of the order of 6 milliampere, then beta DC is equal to 6 milliampere by 0.06 milliampere. So, this is 100. Beta is very high, and normally for the commercially available transistors, we will see that beta is one of the most important parameter for a transistor. In all analysis, beta will be there. So, beta in general varies for all practical transistors in the range say 50 to 400. There is a large number of transistors and they have different parameters. Similarly, this is the value which goes almost in this range. Then what is the relationship between alpha and beta? If we know one, other can be calculated. So, there has to be a relation between alpha and beta. So, we derive, this is a very simple relation, we can derive it and we write the relation between the current gains alpha DC and beta DC. The fundamental equation, that how the three currents are related in a transistor, this we know that fundamental relation is IE is equal to IC plus IB. You will recall that the emitter current breaks up into two regions. One is the base region where some of the electrons gets recombined and which are responsible for the base current, and the remaining one, say 99% electrons, they have crossed over to the collector. So, IE has is made up of IC and IB, and now this can be written as IB or IB is equal to IE minus IC. If we write in terms of changes, then we can simply write change in IB is equal to change in IE and change in IC, and this can be written as delta IB by delta IC. This is equal to delta IE by delta IC minus 1. Now, this is inverse of beta DC. So, this is 1 by beta DC, and this is inverse of the alpha DC. So, 1 by alpha DC minus 1, or this is equal to 1 minus alpha dc by alpha dc. From here we get the relationship that beta dc is equal to alpha dc by 1 minus alpha dc. This is simple relationship which we use to get the value. If alpha is known, beta can be found out, or if beta is known, then alpha can be out. From this equation we can write also alpha in terms of beta, that is alpha dc is equal to beta dc by 1 plus beta dc, and as you are seeing that this will be slightly less than 1. The values of for example, if alpha dc has a value of 0.99, then using this equation we can get beta dc is equal to 0.99 by 1 minus 0.99, which is equal to 0.99 by 0.01, which is 99. Many times, because this is close to 1, so beta dc is taken approximately, and this is within few percent, and the tolerance of few percent is very much acceptable is accepted in electronic circuit. So, this may be taken as approximately as 1 minus alpha dc. If we use this data, it will come 100. So, error of just 1%, but it may be 2% or so in other cases. So, this was about the relationship between the current gains. While we have talked about 3 circuits, common base circuit, common emitter circuit and common collector circuit, we will study all these 3 circuits in details, and we will realize that out of these 3, for various reasons, one reason you have seen here, that current gain in common base is very small, but current gain in common emitter is very high. This goes in favor of common emitter circuit, but there are many more important features of common emitter circuit. So, common emitter circuit is most widely used. Now, we derived a relation for the current, collector current in the case of CV circuit earlier. Now, we should have a relation of the output current, what is the total output current in the case of a common emitter circuit, and again there are some hidden important point in that. So, this is total emitter current in a common base, common emitter circuit. You will remember that we arrived at an expression for total current in common base circuit, and this was equal to alpha I e plus I c b o. We said alpha is a constant, and now we know what this alpha stands. Alpha dc is one and the same thing. Actually, why we have put a dc? When AC is superimposed on the circuit, for example, we are interested in the amplification of AC signals. So, AC signal will be superimposed over DC. So, then there will be a small variation in these values, and that is known as simply beta, or alpha, and when we talk of H parameters later, then this is same as HFE, beta is same as HFE. This is forward current gain in common emitter circuit. But anyway, so alpha we talked that alpha is the current gain. Now we need a relationship between IC and IB for CE circuit, a relationship between IC and IB is required. This we can have in this equation. We call it, for example, equation 1. We substitute IE equal to IC plus IB. We put this here in the first equation, then we get IC equal to alpha IC plus IB plus ICBO. And you will remember this factor was there because the collector junction is reverse bias. And why we put O? Because this is measured when the emitter circuit is open. For example, we can take this arrangement. This is IE is kept 0, this is open, and here this is ICBO. When we apply the reverse bias voltage to the collector, then this is the current which will be flowing, and we can measure by putting a emitter, for example, in series with this circuit. So, this is that, and now this equation we continue, we further look at it, and this can be put in this form. IC is equal to alpha 1 minus alpha IB plus 1 minus alpha ICBO. Using the relation for beta, beta is alpha 1 minus alpha, then this equation becomes IC equal to beta IB plus beta plus 1 ICBO, and this can be written in the form beta IB plus ICEO, where we have put ICEO for beta plus 1 into ICBO, beta being very high in comparison to unity. So, this one can be neglected here. So, this is very closely equal to beta into ICBO. This is something significant that we have talked earlier, that the useful current is only this part. This part is a parasite, does not play important role, but now in the common emitter circuit this becomes much higher. In this case it was in the common base circuit it was simply ICBO, but in common emitter circuit which is under discussion at the moment, this is amplified by beta times. So, this is to be noted, and our effort should be to reduce the value of ICBO itself as much as possible, and when there are other corrective measures which we will be talking. So, this is about the total current in the common emitter circuit. We talked about the fundamentals of transistor and even processes, the alloying process and diffusion process, which are used to fabricate transistors. And we have also talked from time to time about what makes a efficient transistor. Let us look at this point little in more details, that is, what makes a efficient transistor. Current gain alpha is fundamental, and all effort should be to make alpha, the current gain, as near unity as possible, and this depends if we go in greater details, then alpha depends on 3 factors. So, alpha is equal to gamma b delta. These are called efficiency parameters. Efficiency parameters. We will discuss one by one. We have said that alpha should be close to 1. That means, all these parameters ideally should be unity. Now, what are these? Here gamma is called emitter efficiency. Emitter efficiency. B is called base transport factor, and delta is called collector efficiency. We will talk about all these 3 efficiency parameters one by one. Remember, our objective is to maintain, to keep the current gain alpha as close to 1 as possible, and for that will the requirement is that all these 3 parameters individually should be close to unity. Now, how we define the emitter efficiency, that is gamma, the emitter efficiency. We have talked about currents earlier, and we have seen that emitter current has 2 components. If we talk either of NPN or PNP, but currently we are talking NPN transistor, then this is defined as total current carried by electrons divided by total emitter current. And this electron component to the emitter current we write as IE, and total current has two components, the electronic component, this we have discussed earlier, electronic component and hole component, and this can be written as 1 minus 1 plus I h hole component and electronic component, and which can be approximated if we take up and expand it, then this will be 1 minus I h by I e. So, obviously, this factor I h by I e, that means current carried by holes should be less and current carried by electrons should be high. And how we achieve in practice that this whole current arises because of diffusion from base region. So, base region, base we keep lightly doped, very lightly doped, that will reduce this whole contribution to the current, and we increase I e is made large by using heavily doped emitter. Now, I am sure you are realizing what was made as a statement earlier. If you remember the first lecture and second lecture, then these points were just stated and it was said that later on things will become clear. So, I am sure now you realize that why the base was kept low doped, lightly doped, and emitter very heavily doped. Similarly, the other parameter, that is the base transport factor B, base transport factor, this measures that how efficiently the electron current in NPN transistor has been transported to the collector. So, this is defined as the ratio of electron current reaching collector divided by the total electron current into the base. That means, the total electron current injected into the base, and this beta, obviously, because of this is reaching collector, this number is slightly smaller because there will be recombination. So, obviously, this base transport factor B is less than 1, but how we can, this is because of the electron loss in recombination in the base, and we can't get rid of that completely. So, how to make this base transport factor close to 1, that we will see. The detailed analysis shows that B is very closely equal to 1 minus half W by L E, where W is depletion width, base width, sorry, W is base width and L E is the electron diffusion length, in the base region. And this base transport factor B to be equal to 1, very closely equal to 1, W has to be low. So, base width we use very small in width here. This was base, this is N P N, and electron diffusion length in the base region should be made high to make this factor still smaller. And again this is achieved by making the base region very lightly doped. The more lightly doped is the region, higher will be the electron diffusion, minority diffusion. Why transistor is called a minority operated device? Because see, electron when injected into base, they in the p region they are in minority. If we talk of PNP transistor, PNP, then it will be the whole diffusion length in the base region. Now, holes will be injected into base and they will be finally collected here. So, this is the holes are also in PNP transistor, holes are in minority in the N region, and the role of electrons in NPN or holes of holes in PNP transistor in the base region, they are minority region, and this is the most significant part in the transistor operation. So, transistor, a BJT, bipolar transistor, is a minority operated device. It is current operated, everywhere we are talking of current, and hence it is a current operative device. Minority operated device, if we talk of the electron diffusion length, this is we are talking electrons in the p base region, which is again here the electrons are minority, as in p and p holes will be in minority in N. So, by making base width low and by diffusing by using lightly doped base region, we can increase the electron diffusion length, making this parameter as small as possible, and hence B will be close to 1. The third is that collector efficiency delta. Collector efficiency delta, this is again for NPN transistor, this is number of electrons collected at collector divided by the number of electrons arriving at collector. In almost well designed transistor, this collector efficiency is very close to 1, it is equal to 1. And how we get 1? Because we keep the collector larger in size than base region and emitter region. This was said in the beginning when we talked about the sizes of the 3 regions. So, in summary, a efficient transistor, the alpha is composed of 3 components, where we have talked that this emitter efficiency can be obtained closer to 1 by making the hole diffusion in NPN transistor less, that means by doping the base lightly. This is the base transport factor, and this we have seen that this to make it closer to 1, it needs base width less and diffusion length of electrons large enough, and that is achieved by keeping the base again lightly doped. And of course, this collector efficiency is closer always for well designed transistors is equal to 1, because there is no loss of electrons. The size of the collector is kept higher as compared to other. So, this is about how we can assemble a efficient transistor. Transistor is a electronic device, and its behavior is governed, and then we will decide various uses. The IV characteristics are important. So, IV characteristics, current voltage, IV characteristics, IV characteristics of a transistor. IV, that is current voltage characteristics. We are often talking about that common emitter circuit is most widely used, common emitter. So, these characteristics we will be drawing for common emitter circuit and bring out the salient features of these characteristics. They are not different. There are some variations at some points in the common base and common collector circuit, but more or less they remain the same. So, it is good enough if we talk about the IV characteristics in a common emitter circuit. So, for a CE circuit, in the laboratory this can simply be done. We can draw these characteristics, and here is a simple circuit. This is a simple circuit to measure the current voltage characteristics of a transistor in common emitter circuit. Here now we should get familiar with the terminology which is used. The collector battery is represented by VCC, the base emitter battery is represented by VBB. The resistance which is connected to base is written as RB, B is the subscript, and this resistance with the collector RC. The voltage drop between base and emitter, emitter is one terminal is often grounded. So, this is the positive voltage drop, this is minus, and this is designated as VBE, voltage drop between base and emitter. Similarly, here this is VCE, and look at the polarity plus minus, and this is the voltage between the collector and emitter. So, let us be familiar with this. Now, there are two sides of the circuit, the input and the output, and accordingly there are input characteristics and output characteristics. Here what I have shown that the input battery has been connected to forward bias the base emitter junction, and this battery VCC has been connected such that it will reverse bias the collector junction. But we can change, if we change it the other way, we will see what impact it will have. Now, first we talk of the input characteristics. Input characteristics. For that, this is plotted, these characteristics are plotted I B as a function of the input voltage V E, and we can plot them here. This is V B E and this is I B, and this is normally in microamperes, for example 100, 50, 0, 0, 50, and here it is 100. This is the voltage, this is 1 volt and 2 volts. Now, look here, we can change the base current I B by changing either by changing this voltage, and we can plot. This is a simply a forward biased junction. You remember that what kind of characteristics we talked when we talked about the forward bias PN diode. So, similar kind of, this is when we keep VCE, that means at the output side this voltage, because now we will discuss that input characteristics are also function of the output voltage, we will talk that. So, this is kept at 1 volt, then we change the voltage and we get the current, and there is a exponential rise, and from here of course we can find out the input resistance of the circuit. Now, if we change this output voltage, say from 1 volt we make it 20 volts, then there is some change in these characteristics. This is for VCE equal to 20 volts. What does it indicate? That for the same voltage, now the current has fallen. Earlier it was this current, now this is this current. So, there is a small fall in the base current. Now, this is because of the fact the base, you know that the depletion width is a function of applied voltage, this we have talked, and depletion region, here there is one depletion region and this depletion width will increase because this junction, collector junction is here, this collector junction is reverse bias. Now, very important point, that the spread will be there and this spread will be more in less doped base region, because in comparison of the collector, this is collector, base is more lightly doped. So, when depletion region broadens because of we have changed the voltage from 1 volt to 20 volts. So, now there is a 20 volts across this. So, if this was the base with 1 volt and this depletion region will be more spread in the base region, because this is more lightly doped region. As a result, the base width will fall, and hence recombination, this is a recombination current, base current is a recombination current, and when base width has fallen from this much to this much, the lesser number of holes will recombine and hence the current will fall. So, that explains the input characteristics as a function of the collector emitter junction voltage. And then the output characteristics, which are much more important than the input characteristics. The output characteristics. The output characteristics. IC, the collector current, the output current is supposedly function of VCE and of course of IB, and I want to remind you that we are talking of CE circuit. And we can plot these characteristics, they are very important, many important parameters which we have been using, they can be calculated, they can be determined from these characteristics, and these are we change IB here. For different values of IB, we measure, first we keep this voltage constant and we measure the collector current by putting a emitter here, and so then we keep on changing that voltage and we get a set of characteristics like this. This is IB, this is in, for example, in microamperes, this is IC, this is in milliamperes normally, 2, 4, 6, 8. And this is 5 volts, 10 volts and so on. This is VCE in volts, and these are the characteristics here. For example, this is IB equal to 0, this is IB equal to 20 microampere, 40 microampere, 60 microampere, 80 microampere and so on. These are the output characteristics. These characteristics, these can be divided into 3 different regions. One region is this, this region left of this curve, and this is called saturation region. Saturation region. Here I will show you that both the junctions are forward bias. Look here, when this VCC, when this is very small, and actually for silicon transistor this is just 0.2 volts. So, when these are the 2 batteries, this is VBB, this is VCC, I have put them just in one line, they are in series. If this is very small if this is very small, then this will be dominating. Very simple. If you take for example a 2 volt battery with this polarity 2 volts, and you connect here a 1 volt battery with this polarity, this is 1 volt, then what will be the effective potential? Difference of the 2 and this polarity will be dominating. So, this will be like this. So, this is negative, and when this is small, this battery will be dominating, and hence this negative, this is NPN transistor, collector is N type. When it gets N battery connection, it becomes forward bias. So, for very small values of this VCE, this battery will forward bias this junction. So, that is why I have mentioned that both the junctions in saturation region are forward biased. This is the region which is to be avoided for amplifying purposes, because here we have already discussed that current, the output current does not vary linearly with input current, and so this is to be avoided and totally. And to check whether the transistor is in saturation or not, there is a condition that base current minimum has to be equal to or greater to I c by beta. So, in general we can write the minimum value I b minimum has to be equal to I c by beta. If this condition is satisfied, then because this state is used in digital electronics, and there we will have to see that the transistor is put to saturation. So, then this condition is used for any circuit. We can find out the currents. We will take one example how to find out the currents in a circuit, and then this condition can be applied to see whether this is in saturation. And the values of saturated voltages, which are also important, VCE sat in saturation for a silicon device is 0.2 volts, and VBE in saturation is 0.8 volts. This is for silicon device, and for germanium VCE sat is 0.1 volt and VBE sat is 0.3 volts. This is for a germanium transistor. Now, we continue with this region. This region is called the cutoff region. This is the region below IB equal to 0. This is called cutoff region. In cutoff region, both the junctions are reversed bias. Both the junctions are reverse bias. How? If we want to go below IB equal to 0, we will have to change the polarity here. So, once we make it, this is p type base getting a negative voltage. So, that junction is reverse bias, and of course, the output junction is already reverse bias. So, both junctions are reverse bias, and here this also we have discussed that in amplification purposes this region also is not to be used. These two regions, the cutoff and the saturation region, are useful and are used in digital circuits when transistor acts as a switch. We will continue the third section of it, that is what is called active region, and we will continue.